Yeah, I'm 25 and I'm blessed to say this how far I've made it. Look how far we made it. This is for my people come from different countries. Then you realize it ain't really what it seems. But you still go hard and that's what I learned to see. Doing the impossible to realize a dream. Paving the way for your family and your kids. Driving in a system not designed for you to win. But you still win, just look at where you've been. But you still win, just look at where you've been. Look at how we made it. Put your hands in the air if you feeling what I'm saying. Look how far we made it. Look how far we made it. Look how far we made it. Put your hands in the air if you feeling what I'm saying. Look how far we made it. Hey, look how far we made it.
Okay, here we go. That's better. So welcome back. This is session 3, which focuses on sediment and nutrients. A little about me. I am your moderator for this session. My name is Eric Dunlavey. I am the wastewater compliance manager for the San Jose Santa Clara Regional Wastewater Facility. That's the largest wastewater treatment plant in the Bay Area, serving about 1.5 million people, and located in the southernmost portion of San Francisco Bay. I've worked for the city for over 19 years now, and the focus of that work has been on a range of water quality management issues in both wastewater and stormwater. I've been an active stakeholder and participant in the RMP since 2003, where I've engaged in nearly every RMP work group at one point or another. And I've served on the TRC from 2006 to 2017, and I currently serve on the steering committees for both the RMP and the nutrient science program. I'll add, just on a personal note, it's really exciting to be back here in person and see everybody at the RMP annual meeting. As others have mentioned, this is the best day of Bay water quality science every year, and that's a statement that I first heard from Luisa Valiela, so I'm giving her full credit for that. It's remained the best day, even over the past couple of years when we've been fully remote, but it's certainly made much richer and deeper now that we're in person, at least in part. So this session, as I mentioned, is about sediment and nutrients, two topics that have grown into more prominent focus issues over the years for water quality in San Francisco Bay, compared to some of the legacy issues that you heard about this morning. We have 3 excellent talks today from Katie McKnight, Jessie, Lacy, and David Senn. There should be time for some brief questions after each talk, but if we don't have enough time after the talks to get to your question, fear not. We will have a moderated session afterwards where there will be 20 minutes to ask the speakers additional questions. So with that, I'll introduce our first speaker, Katie McKnight, after I drop her bio. Katie is an environmental scientist at SFEI. Her work focuses on geomorphic processes in Bay Area rivers and wetlands, with particular focus on shoreline adaptation and sediment management. Her work also examines how landscapes have changed over time, and she uses this information to guide landscape scale visions to improve fluvial and tidal ecosystems. In addition to her technical research, Katie also serves as a design lead and is passionate about creating illustrative visualizations to make technical information more accessible to all. Katie's presentation to us today is on the sediment conceptual model for San Francisco Bay.
Can you hear me? Oh, okay, it works. And can I stand back here? Is that, you can still hear me? Okay, great. All right, hi everyone. Thank you for that introduction, Eric. As Eric mentioned, my name is Katie McKnight and I'm with SFEI. And today I'm going to be presenting about an exciting project we've been working on called the Sediment Conceptual Model for San Francisco Bay that my colleagues, Scott Dusteroff, he's here today, and others from SFEI have been working on. And we're developing this for the RMP sediment work group, but also more broadly for our RMP stakeholders. So I'm pretty excited to be here today on this wonderful celebration of bay water quality. So as most of you are probably aware, sediment plays an integral part of sustaining our ecosystems in the San Francisco Bay. And there are three considerations of sediment that are critical when it comes to monitoring and managing sediment in the bay. The first of those is building baylands. So the tides transport sediment onto the baylands, which are the continuum of habitats subject to tidal action, like tidal marshes and mudflats and shallows. And as sediment deposits, the baylands are able to accrete in vertical elevation, which is critical to keep pace with sea level rise. And baylands also play an important role in protecting our shoreline from erosion and overtopping by attenuating waves and providing other ecosystem services. Sediment also transports contaminants around and within the bay, as many of you are aware, and we've had several talks today about that. So this really makes sediment management a bit tricky. As contaminants from urban runoff, wastewater discharge, and other sources enter the bay, they get stuck onto sediment particles, as highlighted in many earlier talks on PCBs. And then the third category is primary productivity. So sediment in suspension in the water column also attenuates sunlight, helping to minimize algal growth and the impacts of eutrophication. And Dave Senn will also be speaking in this session on this issue later today, given how timely a topic it is for our community. So while all three of these considerations are important when it comes to sediment monitoring and management, my talk today is going to focus on just this first consideration. So sediment making its way onto marshes, mudflats, and other baylands habitats. So you may be wondering, what do I mean when I say sediment conceptual model? So this effort is really focused on creating an abstraction of how sediment moves around at different scales within the bay, to organize existing information while also highlighting knowledge gaps into easy to understand visuals and diagrams. And so the hope here is that we will be able to provide a tool to improve current and future bay sediment management efforts. So why are we doing this? There are several specific needs that we're trying to answer. So the first is we have a lot of data on sediment transport pathways and rates for current and future conditions to help with restoration planning decisions. And this conceptual model will synthesize a lot of that data. Second, the sediment management and bayland restoration communities need a communication tool with digestible conceptual models that focus on magnitudes as well as uncertainties for sediment transport within the bay. And third, the Bay RMP has limited funds to address questions regarding sediment loading to the bay and sediment delivery onto marshes, which are questions that the RMP sediment work group are really focused on answering. So this conceptual model will help clarify where we might want to focus some of those resources. So the main objective of this effort is to first provide a conceptual level common understanding of the dominant sediment processes for open bay and tidal wetland planning. And a key part of this effort also is about highlighting, like I said, the key sediment process data gaps, distinguishing which parts of sediment movement we have a really good understanding on, and there's a plethora of data for, and then which parts are not so well understood or would benefit from more research, and which kind of fall in the middle of that gradient. The funder of this particular effort is the Supplemental Environmental Project Funds through the Bay RMP. And our intended audience is for all of you, the Bay sediment management community and bayland restoration practitioners, as well as RMP stakeholders and Bay water quality management community. And so we're not starting from scratch with this effort, as many of you know and have probably contributed to. There is a lot of great existing data on sediment transport and kind of conceptualizing our understanding of how sediment moves around at different parts of the Bay. Such efforts include the Sediment Accounting 101 study by Dave Schulhammer and others at the USGS in 2005, the conceptual model of sand transport pathways by Patrick Barnard and others from 2013, the conceptual understandings of sediment outlined in the Bayland Goals update from 2015, and a study by Jessie Lacy and her colleagues at the USGS developing a conceptual model for sediment transport regions at the Bay, at the marsh edge, which she'll be presenting on today directly after my presentation. We also are leveraging a lot of other efforts that have either recently been completed or are in process. These include the Army Corps' gaps analysis, which will identify research priorities that support sediment placement decisions, as well as BCDC and the State Coastal Conservancy's sand budget transport analysis, which will update the contemporary sand and silt/mud budget at the Bay and subembayment scales. We're building on the Bay RMP's watershed dynamic model, which is a new tool for estimating sediment supply to marshes from adjacent watersheds that I think Jay mentioned earlier. And also the Bay RMP's recent sediment monitoring and modeling strategy, which includes more data sources and overall data synthesis. So this is just one list, and then we have other efforts that we're building on as well. We've also been working with several technical advisors and management advisors who have been really key to providing valuable feedback throughout this process. So this is our list. So thank you all to who have contributed and continue to contribute. And so this project, our approach is really to conceptualize sediment, how sediment moves around at 3 scales. The first is focusing on the Bay scale model, showing net sediment flux direction and magnitude for both future and current conditions. Then we will zoom into the subembayment scale, showing sediment sources, fates, and pathways. And finally, we will zoom down to the Marsh-Mudflat scale, showing net sediment flux direction. And for the sake of time in this presentation, my focus will really just be on these 2 bookend scales, so the Bay scale as well as the Marsh-Mudflat scale. So now let's jump in to some methods and preliminary results at the Bay scale. So developing the Bay scale conceptual model follows 3 steps. The first step is to compile existing data on the loading of sediment flowing from the delta into the Bay, from the local tributaries flowing into the Bay, and understanding the magnitude of sediment that flows between subembayments and at the Golden Gate, which I'll refer to here as flux, for both the current and future conditions. And the blue box here on the right lists some of the primary sources we're going to use to do this. Next, we will use that information to categorize net fluxes by their relative magnitude. So for current conditions, we look at how flux varies seasonally between wet years and dry years. For future conditions, we consider how flux changes annually between a wetter climate future and a drier climate future, since we aren't sure how climate change will play out. And then the final step is developing graphical depictions of net fluxes around the Bay by both relative magnitude, so how much sediment is moving and in what direction, and relative uncertainty, so how many data sources do we have to underpin what we're saying about magnitude and direction. So now onto our preliminary results of current conditions and average net flux at the seasonal timescale. The base map here shows our study area and the 5 subembayments we've divided the Bay into, which I'm sure many of you are familiar with. So moving from the Delta to the South Bay, the subembayments include Sassoon Bay, San Pablo Bay, Central Bay, South Bay, and Lower South Bay. Then before I walk through the preliminary results using a series of arrows to indicate net flux, I'll just take a second to explain the legend because we will have a lot going on here. The arrow with the arrow on the top of the screen here, use the pointer for everyone online. That arrow with the black arrow inside of it indicates average net flux between subembayments and at the Golden Gate. And then the more simplified arrow underneath that indicates the magnitude of sediment from local tributaries and the delta. And then next, there's this range of arrows with different sizes, and that is indicating the magnitude of sediment in million metric tons into these 5 bins. So the largest being 2 to 9 million metric tons and the smallest 0 to 0.1 million metric tons. And then the lower color gradient is trying to indicate data richness. So the lighter the arrow, the less data we have to go on in terms of sediment magnitude and direction. So I'll have a quiz at the end of this, so make sure you're paying attention. So here we have the results of the wet year, wet season on the left, shown in blue, and on the right, we have the results of the dry year, wet season, shown in orange. So the arrows indicate flux from the delta, flux from the local tributaries, and flux between subembayments and out the Golden Gate. And the main difference here is that the arrows in the wet year, wet season are larger in the tributaries as well as between subembayments. So now let's move on to the dry seasons conceptual model. The arrows showing tributary loads go away since those are negligible in the dry seasons. During the dry season, fluxes between subembayments are looking about the same magnitude between the wet year and the dry year, with the direction change between the South Bay and the Lower South Bay down here. And there are also many question marks signifying data gaps about the magnitude and direction of flux at the Carquinez Strait and at the Golden Gate. So there are lots of things we could talk about. And so I know I'm glossing over a lot just for the sake of time. But some high-level takeaways are that sediment delivery into and out of the bay is much higher in wet years and wet seasons, and that we have a limited understanding of flux between subembayments and at the Golden Gate due to a well-known lack of monitoring and modeling data. All right, now the maps get a little more complicated. This is looking at future conditions at the annual net flux time step rather than seasonal. The wetter future is shown here on the left in blue, and the drier future shown here on the right in orange. We now have 2 different colors for the arrows for each map, which indicates the time period that the magnitudes reflect. So the light blue corresponds to mid-century estimates from present day to 2049, while the darker blue corresponds to late century estimates for sediment loads from 2050 to 2100. And on the right, mid-century is depicted in yellow and late century is depicted in orange. The wetter tributary arrows are larger for both time periods, in particular in the North Bay. We also see more question marks because we don't have any modeled future conditions for subembayments and Golden Gate flux for these climate futures. So again, lots going on here. And I do want to mention that this data comes from the Sediment for Survival report, which is published, and you can check that out if you're interested. And then we'll also be adapting some of this and adding to it in this work as well. So some of the high-level takeaways from the future conditions include sediment delivery to the North Bay could be much higher in the wetter future compared to the drier future. And we will have no modeled predictions of future flux between subembayments and at the Golden Gate for these climate scenarios. And that presents a big data gap if we want to manage sediment in the bay with climate change in mind. So now let's zoom in to the Marsh-Mudflat conceptual model and talk about our methods and preliminary results. At this scale, we're focusing on the general processes and pathways of sediment with a, with a narrative description of it moving between each possible phase. So we're focused on the relative differences based on geography of the bay, as well as different timescales. And we're going to be more data limited here than the previous scale, just because that's the nature of the data we have to go on, but we are building off of the data sources shown in the blue box here. And then similar to the last model, we'll be focusing on key data gaps to help flag where research funding is needed. So this is the Marsh-Mudflat scale conceptual model, looking at current conditions at 4 locations, out of the watershed and into the tidal zone, down into mudflats and out into the bay, and back up onto the marsh plain. So large storm events, which typically happen during the wet season, cause sediment to travel down local creeks towards the tidal zone. Some of that sediment will make its way onto marshes if they are tidally connected, while additional sediment will move out towards the bay due to levees or other shoreline hardening that prevents deposition of sediment onto marshes. Some of that will go into large tidal marsh restoration projects where levees have been breached. Some sediment will then continue on out into the bay, into the erodible bay sediment pool, while some will deposit directly onto marshes. Wind waves and currents will resuspend some of that sediment deposited into the bay sediment pool onto mudflats or out into the deep bay. And then some of that sediment will continue on via the tides and wind waves to be deposited onto the marsh plain directly over the edge of the marsh or by way of the tidal slough. And then a shoreline erosion along the edge of the marsh will cause some of that sediment to be resuspended and transported onto the mudflat below or out into the bay sediment pool. So again, lots going on here, but a couple of take homes is that this is not linear. Sediment moving to the watersheds onto baylands, surprise, not a linear process. So to borrow a phrase from Brenda Gaden, it's like a washing machine with sediment moving around, and you're not really sure where it's going to end up. In addition, we have limited data in the bay for many of the processes described at the Marsh-Mudflat scale, which will be critical to manage sediment under changing conditions. But we know that this is a pretty simplified process of how sediment moves around, and it's not so simple. Other variables that will affect sediment transport at this scale include relative elevation of the marsh, the degree of shoreline hardening, the marsh's channel density and complexity, the magnitude of local sediment supply compared to local demand, wind wave energy, the trapping efficiency of the marsh vegetation, and whether the marsh scarp is concave or convex as an indicator of marsh edge erosion or progradation. I mean, there's so many things to consider. So we're going to try to bring in a lot of these into our narrative and think that through. So I'll quickly close by going over a few next steps. Our technical advisory committee and management committee will have a chance to review our final draft before we finalize it. And that's happening hopefully in November. After that, our final report will make its way into the world, so keep an eye out for it. It will then hopefully be a useful communication tool to help develop a shared conceptual understanding of what we know and what we don't know about how sediment moves around at different scales. And then the data gaps identified in the report can be used to make the best use of limited resources to address these questions regarding sediment flux and deposition to the bay and sediment delivery to marshes, to ultimately help us keep our baylands habitats healthy and around for many decades to come. So big thanks to SFEI and our project team, and thank you for listening. And I think I'm out of time. I don't know. Yeah, okay.
Thank you, Katie. Really nice presentation. I think because we got back from and started late from lunch, we'll hold questions for Katie until the moderated session. So our next speaker is Jessie Lacy. Jessie is a physical oceanographer at the Pacific Coastal and Marine Science Center of the U.S. Geological Survey. She conducts research on hydrodynamics and sediment transport in estuaries and coastal waters. For the past decade, her research has focused on sediment dynamics in the shallows of San Francisco Bay and sediment transport between shallows and marshes. And Jessie's presentation to us today has a very interesting, very interesting title. It is on sediment transport at the Marsh-Mudflat scale, Whale's Tail Marsh in South San Francisco Bay.
Hi, everybody. It's great to be here in person and see you all. It's my first time in this building, so I just want to say what a great space it is. And thanks so much to Katie for setting up my talk, for that talk was just a great background to what I'm going to talk about. And when I thought about her presentation, I thought that one of the things we're doing in the study I'm going to be describing is really kind of fleshing out that conceptual model at a specific site. So that's what the name of this is trying to indicate. This was an RMP. Oh, here we go. This was an RMP special study for 21-22 that came up through the sediment work group. I want to acknowledge that this is a collaboration between our USGS Center, the Western Ecological Research Center, which is another part of USGS, and that group's led by Karen Thorne, and also UC Berkeley. And while the core of this study was funded by the RMP, it is another example of a partnership. We were able to expand the study through funding from a couple different programs at USGS. So I want to acknowledge that as well. So what are we trying to do here? At the biggest level, one of the RMP sediment work group, that's what SWG stands for, sediment work group's management questions is how much sediment is passively reaching tidal marshes and restoration projects, and how could the amount be increased by management actions? I'm just going to try to increase this window while we're talking about increasing. Here. So we've learned from research that we've done earlier, and China Camp Marsh was where we kind of started on this problem, that we really need to know more about how tidal and wave conditions in the shallows influence sediment delivery to marshes. So we know that in order to survive as sea levels rise, marshes need to import sediment from the adjacent shallows. But in fact, we don't really know that much about exactly under what conditions that happen and what conditions are favorable to sediment delivery versus more erosive. So we're interested in sediment supply through tidal creeks, which has been kind of the focus of marsh research for decades. But one of our foci at China Camp was to try to think about this bay-marsh interface that we have in many of the marshes in San Francisco Bay, where the bay edge is actually exposed to waves, and what happens to sediment supply across that edge. And then we also want to acknowledge that there's also an issue of sediment loss due to waves, and you can see that you can see this kind of erosion in the steep scarps of some marshes like that shown here at Whale's Tail. So our specific questions that we wanted to address are how do deposition and erosion in a salt marsh vary with tides, wave conditions, and season? And then more broadly, what information do we need to predict sediment deposition in a salt marsh? Because that is what we would like to do to plan restoration actions and to choose what marshes to restore or preserve. So we think we need to know suspended sediment concentration in the shallows, but exactly how important is that, and where and when do we actually need to measure that? What other site attributes do we need to know about? The wave climate, the marsh edge morphology, the vegetation density or type. And then another way of really saying that same thing is that we want to collect data to support development of not just conceptual, but actual numerical models of marsh resilience. So the site we chose for this is the Whale's Tail Marsh South in South San Francisco Bay. And you can see where it is in this slide. It's just south of the San Mateo Bridge on the eastern shore. And we were specifically looking for a site with large wave fetch because of this interest in the wave-driven processes at marsh edges, which is understudied. We're also interested in this area because of the proximity to all the ongoing marsh restoration in South Bay in the Salt Pond Project. And we were looking for a site with a steep scarp and erosional edge, which we did find there. So we collected a lot of data. I'm not going to tell you a lot of detail because I want to get on to results, but we worked in 2 study periods, the winter and summer of the summer of 21 and then the following winter. We measured marsh edge erosion marsh edge position in order to track erosion. Then in the shallows, we measured suspended sediment concentration, water level, waves, currents, both in the subtidal and intertidal shallows. In the tidal creeks, we measured water and sediment flux. And we also, out in the shallows and in the creeks, measured sediment grain size and bulk density. And then we took a variety of measurements up on the marsh plain. Oh, so sorry, I should have been showing you this. This shows you that's our tidal creek stations. And now we'll be moving on to the, the marsh plain measurements. So we established transects, a set of transects parallel to the bay marsh edge, and also other transects parallel to tidal creeks. And along those transects, we measured deposition and accretion of sediment. And you can see that in the little orange lines. And on those same transects, we measured vegetation. We characterized the vegetation in terms of percent cover and density and height. And then we also, up on the marsh plain, measured sediment concentration, wave heights, and water level. So I'm going to start now. We're going to get into looking at some of the data. And this is just showing you some of the data in the shallows. And the main message here is just the most important difference between the summer and the winter. And that is the waves and the wind and the waves that the wind creates. So on the summer panel in red, you see significant wave height, and you can see that pretty much every day in summer, we have wave heights over 40 centimeters outside of that marsh. And you can see the suspended sediment concentration. There is a spring neap cycle in addition to the wave-driven sediment resuspension, but you can see that it's consistently very high. In the winter, in contrast, we have these intermittent storms. And you'll remember that this was last winter. We had a couple good storms in December, and then it was very dry. So you can see those, you can see those two storms there in December. So this is the big contrast between the two seasons. And now I'll talk about what we found as far as edge erosion. So our method for measuring the marsh edge was we used aerial imagery and structure for motion. So first we install ground control points that are surveyed in, and then using structure for motion and the imagery, you can see an example of how high resolution the imagery is here on the right. We created high resolution digital surface models of the entire marsh surface. So this can be problematic in marshes because it detects the top of the vegetation as opposed to the earth's surface. But on the unvegetated scarp, you are getting the earth's surface. So we were able to use it on the scarp to track erosion. We decided to do this every 3 to 4 months to see what we would detect. At the beginning, we didn't even know if we would detect anything on an annual scale, but in fact, there was clear erosion of the marsh edge. So this GIF isn't moving. Yes. If you watch that edge, you'll see those are the sequential images of the marsh edge. And in this lower panel here, that is showing you near the area where our instruments were, what the marsh edge looked like at 4 different points in time. And if you were to zoom in on that, you would see that there was close to 2 meters of erosion in that 1 year. So this now summarizes the retreat rates that we saw. And the main lesson here is that the summer and spring were significantly more erosive than the rest of the year. And that, of course, corresponds to the season of the daily sea breeze. So this is quite different to what's seen on the outer coast, where erosion is typically associated with winter storms. It was also gratifying to see that if you look at the second entry there, May 21 to May 22, the annualized rate, and these are all annualized rates, was about 1.5 meters of erosion. And we also used LIDAR from earlier, starting from 2004 to derive an annual rate, and that was 1.6 meters per year. So it's not significantly different in this past year, and it looks like that's a pretty solid number. Okay, so then moving on to what we've seen in the tidal creek measurements. So we had 3 sites. I'm only going to be talking about the main one at the biggest tidal creek, and we measured water discharge, sediment concentration, water depth, and then from discharge and sediment concentration, we can calculate suspended sediment flux. So that's the movement of sediment back and forth in the creek. And so I'm just going to be showing you the results from winter. And if you look in the upper panel at the light gray trace, that's an indication of the spring neap tidal cycle. So when that value is high, that's spring tide. So that's when we're seeing the most marsh inundation and the biggest tides. The blue trace is showing you cumulative sediment flux in that creek. So the big negative slope means that there's big export from the creek. So what we saw is that during the spring tides, which is the time when the marsh is inundated the most, and we expect a lot of deposition, that actually in the creeks, we're seeing a whole lot of export. So this is close to 100 tons of export during that first spring period. Now, much of that came back again over the next 2 weeks where tides were not as energetic, but then we saw export again. So we saw this at China Camp also, significant export during king tides. That doesn't mean the marsh that it's coming off the marsh surface, but if you want to use tidal creeks as an indicator of what's happening on the marsh surface, I think this is a big cautionary note. Okay, so then we also measured sediment deposition on the marsh using sediment pads, and this is the work of Karen Thorne's group. In each transect, in each region, so each region means bay transect, creek transect, interior transect, as shown on the the larger scale map. And each one, we had 3 individual transects with 6 to 7 stations per transect and 3 replicates. And every 14 days, those sediment pads were collected. So we get measure of deposition on the spring neap tidal time scale. And this is what those sediment pads look like. They're very simple. They're really just tiles with these filter pads on them. They get picked up and we measure how much sediment is deposited. And note that if you're at an erosional site, it can't measure anything. The smallest number you can get is 0. So what did that look like? So first we're looking at the temporal variation in deposition. So this is now averages across each transect, just one number per transect. And the big lesson in this slide is that summer's in red and winter is blue. At all the transects, there was much more deposition in summer than in winter. And the second point is that there was a very clear cycle where the 14-day periods that encompass the spring tides had much more deposition than the others. And again, this is not surprising because during the others, there was very little inundation at all. The deposition was greatest on the channel transect and lowest on the bay transect. And that actually is different from China Camp. There was more sediment deposition in the bay transect at China Camp. Now we're looking distance from source. If you've looked at data like this before, you may be more accustomed to this type of view. So as we expect at all sites, there's most deposition adjacent to the source and it decays exponentially going away from the source. The one exception, I don't know if I have a pointer, but if you look on the bay transect in summer, you can see that the peak is not right next to the bay. It's actually set back a little ways. And that's because the wave erosion right at the edge is actually sweeping sediment away. And so we get this deposition in a much broader peak that's moved inland. So now I'm going to show you how this deposition relates to conditions in the bay. And to do that, I'm taking a distance weighted average for each of these transects. Oops. Okay, so first we're just going to look at how does it vary with sediment concentration. And if you look on the bay transect on the left, you see that we have an R squared of 0.92. So it's a very strong relationship between sediment concentration in the shallows and deposition up on the marsh. Not surprising. I think this fits with our conceptual model of what would happen. At the channel transect, we still see a relationship, but it's not nearly as tight. Now, if we think not only of sediment concentration, but we multiply that by inundation hours, so now we're taking into account how long the marsh is inundated in each of those cycles as well, We see about the same relationship on the bay, and then gets a little bit better in the channel transect, especially at those lower concentrations. That looks like a much stronger relationship. Then if we step back and say, okay, if we try to predict this not based on sediment concentration, but just on wave energy, how does that look? Again, a very strong relationship on that bay transect, and positive and significant, but much weaker on the channel transect. Okay. So we can also use this data to start to think about the overall sediment budget for the marsh. So if we use that entire marsh surface to not just look at the retreat along each transect, but to calculate a volume, it turns out that 3,048 cubic meters of sediment were eroded in the 1-year period, and that's about 2.38 tons. Now, if we take that number and assume it would be evenly distributed over the marsh, and we had equal deposition on every day, that would come out to 8.7 grams per meter squared per day. And that's the units in the previous slides I was showing. And you may not remember, but the y-axis was from 0 to 50. So this number is the same order of magnitude as the deposition that we are seeing. So that doesn't mean that it's necessarily the same sediment that's coming from the edge and being deposited on the marsh. But if you want to think about overall, is this sediment gaining or losing? We're talking about similar orders of magnitude, and we're going to be doing more work to also hone these estimates. So the relative importance of the factors that we've talked about obviously vary from marsh to marsh around San Francisco Bay. So the subsequent year, working with the sediment work group, we started a new project to look at some of these processes at 2 additional marshes. So one of them is the San Pablo Bay National Wildlife Refuge, and the other is Corte Madera Marsh. And so we expect these processes are going to vary depending on proximity to the delta or local sediment sources, on wave exposure, marsh edge type, vegetation type. So these studies, we're doing much less intensive data collection, but we're going longer duration. We're trying to do the full year. I'll just show you some pictures of these so you can see how different they are. Obviously, the San Pablo Bay site is closest to the delta. It's also close to the Petaluma River. It has very high wave energy, but the edge is completely sloped, ramped edge, we call it, with fringing spartina. Corte Madera has a small scarp, and then you've already seen the whale's tail scarp is over a meter. I was going to present some preliminary results, but I think I'll skip that and get to our conclusions. So at Whale's Tail Marsh, what we've seen is that the edge is eroding laterally, and the rate of erosion is clearly greater in the summer than the winter. We see that the tidal creeks are exporting sediment, especially on king tides, and yeah, the rate is greatest during the spring tides. We're seeing deposition on the marsh plain that's clearly greater in summer than winter. It increases with inundation time, and it's greatest on the creek transect. So overall, what we're seeing is that this increase in wave energy in the summer leads to higher sediment concentration in the shallows and greater deposition on the marsh edge, but also greater erosion of the marsh edge. We are continuing to think about, there's both an indirect and a direct explanation. You can either think of that sediment directly coming off the marsh and going on up on top of it, or perhaps just being reintroduced into the available sediment pool and then becoming available for later resuspension. But at any rate, that marsh edge is certainly feeding the available pool of sediment for resuspension and transport. Thanks.
Thank you, Jessie, for that really nice presentation. Again, please hold questions until the moderator. Thanks, Dave. I'd like to invite our 3 panelists up for Q&A now, since we have some additional time. Oh, do you have extra slides, Dave?
Oh, no. Oh.
Or am I going the wrong way? There we go. So do we have any questions for the panel? Or anything from online?
This question is for Jessie. I was thinking about the fluvial contributions because I'm a mostly fluvial sediment person. So in the marsh you investigated, what's like the watershed area and how much, you know, even proportionally fluvial input? And also it looked like you you missed the October 2021 event, and I know it was, you know, the first larger event, but no antecedent moisture. So I'm not sure how much flow and sediment it resulted in. And maybe even with your knowledge, comparing that to the China marsh, like if you can speak conceptually about fluvial and tidal interactions, I'd like to hear your thoughts.
So the biggest fluvial source close to Whale's Tail is Alameda Creek, which is, you know, it's a big source, right? But it does not flow directly into the marsh. So I think in Katie's conceptual model, she had this picture of sediments going out to the bay and then serving as a source that is then brought in through the tidal channels. And I think in most Bay Area fringing marshes, that's a better conceptual model. I'm sure there are cases where there's watersheds going directly in. So at China Camp, there is a watershed that comes in on the landward side of the road, and that's probably important to those marshes that are landward of the road. But again, I think the sediment fluxing in and out of the tidal creeks that don't really have a watershed, they're really driven by the rise and fall of water in the bay, is a much more important source for most of our fringing marshes. As far as the October 21, it's true. We wanted in the Whale's Tail study, what we wanted to do was fairly high frequency measurements. So those collecting the sediment pads every 2 weeks. I don't think it's happened anywhere else in the bay before now. We wanted to try to capture the tidal timescale, both daily and spring neap and sort of wind wave event, those timescales, and we did not sample all year round. We sampled for 8 weeks in summer and 8 weeks in winter. So we missed a lot.
Thanks. Tom.
For Katie. Okay, I'm the second time I've seen a presentation on a conceptual model, and one finding, preliminary finding that's so I'm challenged with has to do with the bay scale is net flux from South Bay to the southern part of the Central Bay, which just seems, I have a hard time intuiting that, especially seems counter to what years ago, like Ray Crone demonstrated, at least from his understanding at the time, the late 70s, net flux south. But I think part of it, it's just illustrating that we still have a lot to learn about embayment to embayment flux, and as well as within the embayment flux, right? So basically, the benefit of the conceptual model, I'm just partly answering my question, is to illustrate sort of this uncertainty and say that that's important, and we need to do some experiments to better understand that, because we all know it's very complicated, so it's hard to simplify it. You can't simplify it, right?
Yes, great answer to your own question. No, I completely agree. And I think one thing that we're thinking about too and asking questions is like, how will the bathymetry of the bay change with sea level rise, and what will that mean for future flux? So not only do we need more data on the current flux for other sub-embayments, and there is some really great data that we're starting with, but you know, what does that look like into the future? And we don't even know what the future will look like. We have different climate models, so running different scenarios. So it is complicated, but it is really important as well, since a lot of that sediment could then either get onto marshes or might flow out like the Golden Gate. And that is just a really important part of the equation.
I think we have a question up top, and then get to you, Jim.
There we go. This question is for Dave. This is Eric Dubinsky from US EPA. I have a question about the termination of the event. I know this is on your list of questions, but is the thinking that it was biologically caused, or does some kind of nutrient limitation play into that? And also, what do you know about the recovery of nitrate after the event? Like, are we back up to where it was before? Or is it how long does it take for the system to reach its pre-event concentrations?
In terms of the termination, it was such an abrupt drop that I'm a bit puzzled to figure out exactly which it is. I mean, we've been looking at imagery from something called an imaging flow cytobot to look at the phytoplankton community and the zooplankton community, and it's a very different community after the bloom terminated. It could be that there were a lot of grazers, that it just took some time for the things that enjoyed eating this heterosigma to grow up enough to actually be able to tackle its population. I think as well, there's viruses or something that is a common thing that takes out harmful algal blooms. And then I think that it could very well additionally be nutrient limitation. In terms of the rebound of the nitrogen, that's been interesting to watch. For one, the water column cleared tremendously after the phytoplankton apparently dropped out of solution into the sediments, and with very low turbidities in the water column after that happened. And I don't know if that's because of some sort of rubbery stuff now on the sediments, or if that was something more like, I think Lorian mentioned to me, someone mentioned the idea of like the way that you would put polymers in the water to clear a clarifying basin and actually drag things out of the water column. So the reason I mentioned that with respect to the nitrogen is that the nitrogen levels have stayed relatively low. Biomass hasn't really jumped up tremendously either, but that can be a bit tricky or sneaky because you can still have a lot of production happening, things being eaten very quickly or grazed on really quickly and not see biomass increase much. And so nitrogen levels have remained very low and they're only gradually climbing back up. I think at least in part because it's being utilized by a different community now.
Jim?
So this is a question for both Katie and Lacy. I would love to see resilient shorelines part of the western face of the eastern East Bay, from Point Canoe down to wherever. But there's a big fetch, and there's daily winds, which I know about pretty well. There was a small scale experiment that was done as part of the mitigation proposal for the Bay Bridge, where Caltrans took out eelgrass. So they tried an eelgrass planting project at the foot of Gilman at a fairly small scale. That sediment's all smeared now; it's all gone. Didn't sustain anything. So the question that I have is, as we start to move modeling to actionable, is what level of experiment would be necessary to develop models and the kind of things that will be useful with the billions of dollars worth of investments we need to make. How do we have to scale this up so we can figure out whether or not we can do that and at what scale? Easy question, huh?
Yeah, I'm not answering your question, but that's not a good area for eelgrass. I mean, it's really turbid. But are you saying at what scale do we have to work on living shorelines in order to?
What's going to survive that kind of environment out there, and how can we be sure that the level of experimentation that we do between now and 2050, 2060?
I mean, I think one of the first questions is, what are the best areas to focus on restoring and sustaining? And is an area that's visibly retreating every year the area you want to choose to protect?
So we're just going to lose them.
Well, I guess we can have a philosophical conversation about that, but I think that's a foregone conclusion. I guess what decade we're going to lose is not settled at all, but the amount of sea level rise that's projected, we're going to lose. I think we need to prioritize. It's also true, though, that those areas are where we need the marshes, where we need protection for infrastructure that's behind that, right? We don't want it to erode all the way back to where we have buildings and highways and so forth. So I don't know. So there is a proposal now to try a strategic placement pilot project in that same area. I think it will be interesting. I mean, I do think we're seeing evidence that at least at some times of the year that there's limitation. There's not enough sediment available. That if there were more sediment available, we'd be seeing more resuspension. If we're seeing more resuspension, then we'd be seeing more deposition. So you know, we can talk about how big that has to be in order to actually see how much difference it would make. Yeah, I don't know the scale, but do you have comments?
Well, I just have one thought. Since we're kind of talking about nature-based solutions, so I worked on a project a few years ago, the San Francisco Bay Shoreline Adaptation Atlas, and in that report, we mapped different parts of the shoreline that are more suitable for specific, you know, nature-based solutions, like where do you have room for tidal wetlands and mudflat augmentation, or where is there not room, or where maybe you focus on subtidal approaches like oysters and eelgrass restoration. And so that's one resource that could help us, you know, figure out what's suitable where, so we don't start down the path of site scale experiments that maybe aren't well suited for a specific place given the bathymetry or the conditions. So that's one tool. And then we also recently, I mentioned this in my talk, looked at our report Sediment for Survival, which was kind of comparing the amount of sediment that our tidal marshes and mudflats need currently and also into the future under different levels of sea level rise. And then comparing that to, you know, what is coming out of our local tributaries and the delta and kind of these larger dynamics going on in the bay. And I think that can also be a tool to think through, you know, where might be more resilient just based on the local supply and local demand kind of ratio. But we know that's not a perfect depiction or projection of what's going to happen, because it is a little more complicated. But anyway, those are just two tools that came to mind. But my head's not really in the experimental piece of it, but I know others on like the sediment work group. I don't know if Scott wants to chime in or Melissa, but that's kind of my thoughts.
Thanks. I do want to give a chance for our remote attendees to ask a question. I think Melissa has some.
Sure, yeah. So this is for Jessie from Craig Jones. So if you look at the aerial imagery for a longer period of time, looking at the scarp at Whale's Tail, do you see a transition from sort of a stable state of accretion to more erosion or accelerating erosion? Essentially, what's kind of the longer term pattern that you see there at the scarp edge?
Well, so we started collecting imagery in May of 21. We don't have, there's LiDAR from earlier, and we are actually, this is one piece of the project that we are continuing, not at the same intensity, but we've decided to do semi-annual, at least for this year. We'll see how it goes. But because there are not that many documented cases where we're really able to measure the rate and seasonality of marsh edge erosion. So, but I don't think we have the data yet to answer that.
Thanks. And I think Tom Hall. Yeah. Okay.
Thank you. Tom Hall with EOAs for Dave. Thanks for pulling together the beginnings of all of that information. It's a lot. wanted to get your thoughts on some sort of integrator or synthesizer getting at the questions of what caused the bloom and why heterosigma, and maybe calling it something like an early warning system. Your thoughts on some way perhaps to, we could integrate or more closely track temperature, insulation, use the cybots to look at the phytoplankton composition. Since the nutrient loading from POTWs anyhow is interesting, you reminded us about the benthic, all the complications that are going on there. But anyhow, that the POTW loading is constant throughout, so there's some type of climactic thing, it appears to me, that's, probably part of the trigger or the trigger. But anyhow, your thoughts on what we might be looking towards in the future to putting together an early warning system.
That's it. You got it.
The early warning system is an interesting idea, and something that I think we need to think about is what would we do if we were warned? And that, I mean, not that it's, I think there's value to having information out, and even if there's not a lot you can do to prevent it, something that's about to happen. But I think that arguably would determine the amount of effort that people would want to put into it to make it. But I do think that, so something that really struck me, I found really interesting was we've been spending a lot of time in developing an assessment framework looking at chlorophyll concentrations that might be able to predict the occurrence of a harmful algal bloom. And one of the things that we observed our colleagues at the USGS, when they were cruising past on the 10th or so, past 10th of August, right past this area that was really cooking on just a few kilometers away, chlorophyll levels really didn't register too much of a blip. But if you looked at the imaging flow cytobot, which is essentially an automatic microscope, takes photos, you could see the organism there. And so in some ways it actually was the other way around, but the presence of the organism might be, or the presence of the organism at a high enough level is already an indicator of it having found some suitable habitat to be able to grow. So I think that's something that we can be looking at, is looking for the organisms and looking carefully at the organisms. We've also, if one of the things that we might actually, if one of the management decisions might be to, let's say, try to emergency adjust loads to the system to try to slow something down, one of the things that we know we would need to look into is how much realistically could actually be drawn down, and what would the effect of that realistic drawdown be on potentially halting an event. On the one hand, I think that if you were starting from a full tank of nitrogen in the system, turning off the wastewater treatment plant loads is not going to have a major effect on the available amount there over the course of, say, days to weeks, or days, let's say. However, the fact that we see the organisms growing really quickly still when the nitrogen is almost gone suggests that they are potentially thriving off of some steady source, and so maybe turning it off would actually have some effect. So I think it's something we definitely need to look into more. In terms of the predictors of, let's say, the climatic variables you mentioned, I don't know that we'll have enough ability to anticipate what's going to happen, say, tomorrow or next week from something like that. I do think one of the questions that I think we do need to ask is, if suspended sediments were low this year, let's say anomalously low, what's the likelihood that they might be anomalously low next year? If, for example, there's a drought component to this where there wasn't a lot of delivery of new material this past year, if we have another drought year, might we have a similar set of at least turbidity-related type conditions? So that's something that I should pass to the people next to me, though, for the specifics on that.
Trend analysis. Just to follow up, I mean, there's not much you can be do in terms of.
We've got to cut the questions off. We're already cutting it. We've cut into our break by quite a bit. So maybe ask your questions during the break of our great panelists. So please give them a round of applause.
Please come back by 3:05.